So today we're going to dive into topology, a field that's often called rubber sheet geometry. And for good reason. It's this incredibly powerful mathematical language we use to describe the absolute essence of shape, completely ignoring things like distance or angles.
Let's start with a really cool idea. Your data has a secret shape. Seriously, any collection of points, whether it's a physical object or an abstract dataset from finance or even neuroscience, it has an underlying hidden structure. There are patterns, connections, and even holes buried inside. And that, right there, is the million-dollar question. How on earth can we analyze the shape of something that's super complex, especially when we can't even see it? Like, what about an object that exists in hundreds of dimensions? Yeah, we're going to need a whole new way to think about what shape even means.
All right, so the first thing we've got to do is frame this problem in a modern context. We want to get beyond just simple statistics. The goal here is to identify the fundamental qualitative properties of a shape that really tell us how our data is put together.
So here's the really important part. We don't care about things like length or how much something curves. We're looking for features that stay the same even when you stretch or twist the data around. In this modern field called Topological Data Analysis, or TDA, this is everything. We count things like connected pieces, loops, tunnels, even higher dimensional voids. These are actually quantified by something called Betti numbers. But to find those properties, we need to understand the #1 rule of topology. What does it even mean for two shapes to be considered the same? And this brings us to the really fun part, the geometry of stretching.
The whole game is built around this one key idea. It's called a homeomorphism. Just think of it as a set of rules for transforming one shape into another. The rules are pretty simple. You can stretch it, you can twist it, you can bend it all you want. But, and this is the crucial bit, you can't cut it, you can't tear it, and you can't glue bits together. If you can turn one shape into another by following these rules, then to a topologist, they're the same. They are homeomorphic.
And this leads to some of the most famous, kind of mind-bending examples in all of math. You know, a sphere can be smoothly inflated into a cube, and you can squish it right back. To a topologist, same object. And even more famously, a donut, what we call a torus, can be reshaped into a coffee cup. That single hole in the donut just becomes the single hole in the handle. Wild, right? Okay, so proving two things are the same? In theory, it's pretty straightforward. You just have to find the right transformation. But what about the other way around? This is the real challenge. How could you ever prove with 100% certainty that no matter how clever you are, you'll never ever find a way to turn a sphere into a donut without tearing it?
To answer that tough question, we need to build a toolkit. These are the foundational concepts that'll let us rigorously describe and compare shapes. We're going to be looking for special properties that just have to be preserved no matter how you stretch or deform something.
It all starts with the bedrock definition of a topology itself. You take any set of points, and a topology is just a way of grouping those points into what we call open sets. Think of these open sets as defining what a neighborhood is. This whole framework gives us a super precise way to talk about nearness and continuity, the language of smooth Z-formations, without ever needing a rule.
Now check this out. It's called the Hausdorff property, and it's basically a simple sanity check. It just makes sure that any two different points can be separated into their own little neighborhoods that don't overlap. This stops points from getting all blurry and indistinguishable, and it's a critical property for the kinds of well-behaved spaces we call manifolds. Spaces that, if you zoom in far enough, look just like our familiar Euclidean space.
All right, another big one, compactness. This basically takes the familiar idea of a shape being closed and bounded and makes it much more general. The formal definition talks about covering a space with open sets, but intuitively it just means the space is a self-contained whole. It doesn't go on forever, and it doesn't have any missing boundary points.
And that brings us to a really powerful idea, homotopy. This is an amazing way to classify loops on a surface. Imagine you draw two different loops on a donut, both starting and ending at the same point. If you can smoothly wiggle and deform one loop until it looks just like the other one, without it ever breaking or leaving the surface of the donut, then those two loops are considered homotopic. They're fundamentally the same.
Okay, now we have our geometric toolkit. We can start to see how these concepts are building on each other. And this is where the real magic of topology happens. We're going to use all this geometry to turn our shape problem into a problem of algebra.
You see, studying homotopy opens the door to this incredible field called algebraic topology.
The core idea is brilliant. You assign an algebraic object, like a group, to a topological space. This object acts like a unique fingerprint for the shape. And if two shapes have different algebraic fingerprints, well, there's just no way they can be the same shape.
And the first, most famous of these fingerprints, it's called the fundamental group, written as pi1. It's a group where the elements are basically all the different kinds of non-shrinkable loops you can draw on a surface. In short, it's a really sophisticated way of counting the one-dimensional holes in a space.
And boom, here's the payoff. This is where our toolkit proves its worth. On a sphere, S squared, any loop you can possibly draw can be continuously shrunk down to a single point. Its fundamental group is trivial, it's nothing. But on a torus, T squared, you've got loops that go around the central hole and other loops that go through the hole. You can't shrink those down. They generate a fundamental group of Z cross Z. This algebraic difference is our rigorous, airtight proof. A sphere and a torus are fundamentally, topologically, distinct.
So with this incredible new machinery, this algebraic topology, mathematicians were finally ready to take on one of the greatest, most stubborn mathematical puzzles of the 20th century.
Let's go back to 1895. The father of topology himself, Henri Poincaré, publishes this seminal paper, Analysis Cetus, that was the old name for the field. And in it, he basically lays the foundations for algebraic topology and poses a deceptively simple question.
He asks this: if you've got a compact three-dimensional space and it's simply connected, which is just a fancy way of saying its fundamental group is trivial, it has no one-dimensional holes, is it necessarily absolutely always just a three-sphere in disguise? It sounds obvious, right? But proving it was a whole other story. The problem resisted proof for an entire century. And in this bizarre twist, the higher dimensional versions were actually solved first. Stephen Small handled dimensions 5 and up way back in the 60s, and Michael Friedman conquered dimension 4 in the 80s. But the original 3D version, the one that could describe our own universe, remained completely unsolved until 2003.
And then it happened. A mathematician named Grigori Perelman quietly posted a series of papers online that finally, after 100 years, solved the conjecture. It was a monumental achievement, and it confirmed Poincaré's original intuition. The simplest possible three-dimensional shape is, in fact, the three-sphere.
So think about that journey we just took, from finding the secret shape of data all the way to solving century-long puzzles about the universe. It shows the incredible power of topology. It gives us a language to describe the very fabric of space itself, which leaves us with one final big question. As our data gets more complex and our models of the universe get even stranger, what other fundamental truths are just waiting out there to be described by the elegant language of topology?